Chapter 12 is on vector-valued functions. The objectives for the first section are to analyze and sketch a space curve given by a vector-valued function, and extend the concepts of limits and continuity to vector-valued functions. For space curves and vector-valued functions, a plane curve is defined as a set of ordered pairs f of t, g of t, together with their defining parametric equations. So we have an equation x equals some function of t and y equals some function of t. We call that a plane curve because the vector-valued function results in a graph that's in the plane with only x and y. A space curve is the set of all ordered triples of f of t, g of t, and h of t together with their defining parametric equations. So you have x equals a function of time, y equals a function of time, and z equals a function of time. And f, g, and h are continuous functions on an open interval. Here's a definition of a vector-valued function for, again, if r of t is a vector-valued function in the plane, if it has the I and j components, just another way to write it, and for space has I, j, and k components. We say that r of t is a vector-valued function. We call it a vector-valued function, and you notice that the r is in bold. That defines a vector. That's the notation we use for vectors. And we call f and g and h component functions. Another way you can write a vector-valued function instead of the I, j, and k, you can use the angle bracket notation. And then by letting the parameter t represent time, you can use a vector-valued function to represent motion along a curve. Two different curves can't have the same graph. For instance, each of the curves given by r of t, which is equal to sine t I plus cosine t j, and r of t, which is equal to sine t squared plus I plus cosine t squared j, has a unit circle as its graph. The same graph is displayed by both of those vector-valued functions, but these equations do not represent the same curve because the circle is traced out in different ways on the graph. And you can sketch using parametric mode on a graphing calculator. You can sketch these vector-valued functions. To sketch r of t, which is equal to sine t I plus cosine tj using a graphing calculator, we want to first change the mode on our calculator to make sure it's in parametric mode. Make that change and then go to the y equals and type in what x of t and y of t will equal. So that's your f of t and h of t. X is equal to sine t and y is equal to cosine t. Then I typically start off by pressing the zoom and start off with a standard zoom, choice number 6. Now you'll see a circle that's traced out. I'm going to zoom in. I'm going to type in zoom 2 and enter to see a close-up of that. And if you press trace, you'll see at t equals 0, the location on the unit circle is at the point 0, 1. Now I'm going to trace to the right, and you'll see that the curve is traced out back to t equals 1.57. That's pi over 2. You get x equals 1 and y equals something very close to 0. This is due to rounding. And continue to trace. Here when t equals 3.14, that's pi, you get the location for x is very close to 0 and the y is negative 1. So that's how the unit circle is traced out with the r of t equals sine t I plus cosine t j. Now let's compare how it's traced out when you're looking at these parametric equations. So I'm going to go to the y equals. I'm going to change the sine t to sine t squared for both the x and the y. And now starting off with the standard zoom, you can zoom in. Okay, you can see that the graphs aren't looking the same, but the resulting graph should look the same. We do have some error here due to rounding and just some limitations of the graphing calculator. If you press trace and you move on, move to the right, the time increases. As time increases, you can continue to increase, and you'll see that at t equals about, well, let's see, you can see that at different times the location on the graphs are different. So one of those points in time that we talked about was at pi over 2. At pi over 2, on the first graph, the location was the point 0, 1, but you can see that definitely a different location here at the same time. And if, again, you can trace and type in pi, and you'll see the location is very different on this graph compared to the other graph. Now, to sketch these graphs, these paths, we think about the vector valued functions. The terminal point of the position vector r of t coincides with the point xy or xyz on the space curve. So our vectors that result from plugging in specific values for time are graphed from the origin to a point on the path. And the collection of all those endpoints on the path create the curve in the plane or the curve in space. The arrowhead on the curve indicates the curve's orientation by pointing in the direction of increasing values of t. Unless otherwise stated, the domain of a vector-valued function r is considered to be the intersection of the domains of the component functions f, g, and h. For example, the domain of r of t, which is equal to the natural log of t, I, plus the square root of 1 minus tj, plus tk. We could say the domain here is all the points in the interval from 0 to 1, including 1. And the reason why we have this restriction on the domain here is if you look at the graph of natural log of t, p must be greater than 0 in order for you to plug in something to get something, a real number out. So the domain of natural log of t is all the t greater than 0. The domain of the square root of 1 minus t is everything, all the values of t that would make this a non-negative number. So that results in everything from 1 and less than or equal to 1. So when you combine those domains, the intersection, you get the domain for the entire vector valued function, or all the t values between 0 and 1, including 1. The example at the bottom of the page here gives a vector valued function, which is 1 over t minus 1I plus 1 over t plus 3j. And the domain here would be all the values of t except for the value t equals 1 and t equals negative 3. At those two values, when you plug those in, you get undefined component. So that means those are the restrictions on the domain. Okay, for this example, we want to sketch the plane curve represented by the vector valued function, where r of t is equal to 2 cosine ti minus 3 sine tj. And the domain here is defined for t to be between 0 and 2 pi. Now from the position vector, you can write the parametric equations. So x is equal to 2 cosine t, and y is equal to negative 3 sine t. Now, if you solve the first equation for t, cosine t, you get cosine t is equal to x over 2. And if you solve the second equation for sine t, you get sine t equals y divided by negative 3. Now we're going to use the identity cosine squared t plus sine squared t equals 1 and make the substitutions to get the rectangular equation x squared over 2 squared plus y squared over 3 squared equals 1. And you should recognize that as the graph of an ellipse. The graph of this rectangular equation is the ellipse that's shown in this figure. Now, if you're just graphing the ellipse, you would need to determine the orientation or the motion along the path as t increases. The curve has a clockwise orientation, that is, as t increases from 0 to 2 pi, the position vector r of t moves clockwise and its terminal point traces the ellipse.